Welcome everyone. For those of you who might not know me, my name is Melody Yu, and I'm a research assistant professor here and also part of the organizing committee for the School of Architecture Public Lecture Series. So thank you very much. And this is actually our third and last lecture for the fall semester. And welcome you all today. And yeah, special welcome to, I think we have some friends from USC, from University of Southern California here. Yeah, welcome guys. Hope you guys enjoying your time here. And then of course, then I have to introduce our speaker today, Professor Ena, excuse me if I mispronounce, Lloret-Fritschi. Fritschi. Lloret-Fritschi. Okay, get a bit better on that. Yeah, anyway, yeah. Welcome, welcome Ena, and she's an assistant professor at the Academy of Architecture at USI, so the Swiss-Italian University in Mondreso, Switzerland, yeah, which I think she'll introduce to us a little bit more later, where she leads the Fabrication Material-Aware Architecture Research Group. So prior to joining the Academy of Architecture in USI, she was a postdoctoral researcher at ETH Zurich, where she pioneered novel approaches in shaping concrete with minimal material use. She also worked at leading architecture office such as OMA, and also the co-founder of Foldcast, which brings together innovation, entrepreneurship, and architectural practice. And for this lecture, titled From Slipform to Thin Formworks for Sustainable Construction, Ena will share with us an overview of a project moving along a gradient of innovation in technology and construction, from building with less concrete towards integrating earth-based material to explore how design, fabrication, and material experimentation can redefine the future of architecture. Yeah, so I'll pass the stage to Ena, and let's give a warm welcome. Thank you.
Thank you. So, first of all, thank you, Melody, for the introduction, and also thank you for the invitation. It's really a pleasure to be here in this very vibrant city and also this amazing university. So thank you for that, first of all. So as already said, I'm leading a lab at the Academy of Architecture in Medrisio in the south of Switzerland, which is called Fabrication and Material-Aware Architecture. Maybe just to highlight one point, because there is always a bit of a confusion where I'm actually doing my research. I'm showing today quite, let's say, a body of research that I have been conducting and leading at the ETH in Zurich, and also in interdisciplinary context between material scientists, roboticists, and also architecture, of course, where many of these things that I will show today have emerged and have been a starting ground for a lot of the work that I also show towards the end. And in 2022, I moved down to Ticino, to the south of Switzerland, where we have a school called Accademia di Architettura Medrisio, which was, let's say, founded by Mario Botta, which is probably a name for many of you in here. So a school that really looks into construction, using hands, using building technology, but on a very, let's say, traditional method. And I'm now there as a kind of a new addition to the school, looking into how digital technologies can also influence the way we build, hopefully in the future. So I gave the name to my presentation today, From Slipform to Thin Formworks for Sustainable Construction. And I think it's always important to be skeptical about the word sustainable, but in this context, I think it fits, while we still have to consider how much of it is really sustainable, and I will get into that also through the processes that we have developed. And let's say the reason why I'm doing the work I'm doing is, of course, because of the architectural industry, where we know that more than 4.4 billion tons of concrete is being produced every year. And this is equal to 7% of the CO2 emissions when we calculate it relatively conservative. Also, we know that concrete requires a lot of, let's say, natural materials and resources to be made. And this is, of course, something we need to start rethinking in a global warming situation, where how much of this material do we need? Can we use less of it, or could we use 50% of it? We would already reduce the amount of CO2 emissions that we are emitting globally. Okay, next slide, I see. Can I just make one change? Because I see that something is on that I don't want. I'm just going to take this for a moment because I think the automation, no, it's not on. No, so, yeah, this I don't want. So,
should be on click.
Yeah, exactly. So, sorry for that. I just hate when things are running in parallel. So let's just do this. It should come now. No, wait. It's okay, you just have to be patient.
Yeah, play again.
Play again? And
Yes.
now it's there. Okay. So sorry for that. It was on automated play, which I don't like. So I think there is a lot of possibilities to reduce concrete, and it's nothing new. It's actually something we know very well from history. And looking at these three examples up here, starting with the lecture hall by Hans Dieter in Freiburg, or the Ponte sul Bassetto by Musmetti, or the Bosch's Chapel that was built in 2018, we all see very nice and exciting examples of how we can actually use minimal surface or optimize concrete structures. However, one of the bottlenecks of such systems is, of course, this very complex formworks that needs to be built, and they resemble a building almost on their own, which are then removed as a temporary structure and mostly ending up as landfill or waste. Also, we have to look at, let's say, historically into how many innovations were happening in architecture in the post-war era, where we saw a lot of patents that were emerging over time. And this is an extraction from the European Patent Office done by the group of Silke Langenberg at the ETH Zurich, trying to put a numerical value onto how many patents were actually filed during this post-war era for building more, let's say, smart in terms of general construction of buildings, structural elements, roofs and coverings, and you name it. They were all patented around this post-war era. And then we see a very heavy decrease and a slight, small wave happening around 2016 and then again going down. So why is this happening? It's also partly because of some of the digital fabrication technologies that were emerging in this period of time, but never been enough to actually make a big impact. And this is probably a little bit, in a way, it's a little bit sad to see that we do a lot of innovation. We're looking into ways to reduce materials. But on the other hand, we see a continuous increase of waste. For instance, in Switzerland, where I have very secure numbers of 84% of the total waste is produced by the construction sector. On the other hand, we can see similar numbers also here in Hong Kong, but I don't have them exact enough to actually state them on a slide, but I saw transferable numbers to Hong Kong in accordance to the Hong Kong Environmental Protection Department website that actually states similar numbers in terms of amount of waste just coming from demolition and the construction industry for the construction itself. And in a way that, to put it in a figure, in this very short second that I show this slide, we've been disposing more than 500 kilos of waste, which is equal to a baby whale, just to give you a bit of a picture of what that actually means in mass. So the question emerges out of these kind of, let's say, the setting of the construction industry, how can we build with less material? And there is a number of people looking into this, and I think the most known one of this is probably 3D concrete printing, which is claiming to be sustainable, claiming to be the new way of building. However, something that needs to be taken into account is the high amount of cement that is contained in these systems that we print, and there is still a lot of work to be done in terms of durability with 3D printing. So to be taken a bit with care. Then we have other systems that are more innovative, or let's say more disruptive, in the sense of using counter-pressure formwork, so trying to minimize the amount of formwork by printing a formwork for concrete to be filled in, and then the formwork is removed and again disposed. And then we have a number of these more thin formworks that have especially emerged within my own research and also the research of Norman Huck within the group of Gramazio Cola, where we've looked into how robots can be used to, let's say, lost formwork production, where we use the robot to spray onto a reinforcement mesh for structural applications later on. And then we have more like digital casting systems, which is my own work that I will be showing you today. And this, finally, together with these stay-in-place formworks, is some of the work that I will be discussing with you. So I think when you want to build with less, you need to consider two main aspects. On one hand, we've seen a lot of people looking into the reduction of materials through making optimized formwork geometries. However, we also need to reduce the formwork itself, as this is also generating high amount of waste. So for more than 10 years, I've been involved in this interdisciplinary work at the ETH in Zurich and now at the Academia of Architecture in Mendrisio to explore methods of how we can actually investigate these two aspects together. And smart dynamic casting, which was my PhD research and also became, let's say, the founding of many of the works that I will show, looked into how we can scale down slip forming, a very well-known construction technique, to actually reduce the amount of material that we use in terms of formwork and concrete itself. However, to make this work required that I almost became a kind of a pseudo material scientist on the side. So I started to work very close with the material scientist department and became part of their group over years to develop a system that allowed us to control material while it is kind of like a clay, and on the other hand, it shouldn't be too hard because we had these two failure moduses in the production, which was either too soft or too hard. So what we did was we made the first kind of, let's say, set-on-demand system, which became also, let's say, a baseline for many of the 3D concrete printing technologies that we have today, where we had material that was pumped, an ordinary concrete with a little bit of sugar to make it soft for a very long time, very well known in the industry. And then we would take this and put it through a pump, and then we would run it through what we call an inline mixer, where we would add a bit of salt, which is accelerator, to control the hydration over time. And this was the, let's say, backbone and backlaying concept of how we could actually control the hydration of concrete in these processes. Maybe one step back. And this, of course, enabled us to do the slip forming, which we call STC, and also the thin formwork that I will show you with paper and also 3D concrete printing. And just a small image of some of the first tests that we did. It was not about twisting a column. That had nothing to do with what we wanted to understand, but what I essentially wanted to understand here was, can I shape concrete almost like a soft ice coming out of the machine as I'm slip forming upwards? And here you see the next step, which was an attempt, a very strong attempt to try to actually shape the material with the goal of shaping it where it's actually needed structurally. And here we see many problems, and it took 20 tests to do this single one column, so obviously it was not very robust, and we had to change the way we did it. And luckily, we were asked to use this slip forming technique inside of the DFAB house at the EMPA in Dübendorf, very close to Zurich, where we then had the chance to further develop the system into what we called the global shaping formwork, where we developed a way of shaping the material while it was still in a fluid condition and still moving upwards, and all automated. And here I'm going to show you a video that gives you a picture of how the entire installation was done. So obviously we went away from the robot, which I see more as a sketch tool for development. And then we developed a linear axis system that one could also envision having inside of a, let's say, prefab plant. You see the entire setup. It's pretty rudimentary in a way, but it's really a prototype. So when you work with new material processes, it really requires you to have a deep insight into how the material is reacting and acting. And on the other hand, it needs you to also develop the end effectors and the tools as well as the software behind it to control the machine. So here you see one of the mullions being produced. You see the material that is accelerated coming out into the, and notice the funnel. There will be another version of this one later on in another presentation part. And here you also see the software where we worked very closely with the architects that together with them, we said always, we cannot tell you what we can design, but we can do a series of tests and then we can give you the design constraints. And with this, we gave them back, let's say, a grasshopper tool where they could define the mullions in accordance to the structural needs of the facade. And every single mullion was then installed inside of the defab house and made for disassembly. And finally, here, here, you see an image of all the innovations that were put together into an ensemble where you see the mullions, where there were all 15 different ones done with a single formwork, with the same material typology, with a single software where we just exported as a numerical machine is controlled into how the formwork should move. And of course, comparing this to a standard process, we could use 30% less material. The roof you see is, of course, from my colleague Benjamin Dillenburger, and the wall is the mesh mold wall of Norman Huck, my colleague that is now in Braunschweig. While we were doing this very exciting work, we also saw that the smart dynamic casting system is coming with a series of constraints in terms of geometry. That can be an advantage, but it can also be a disadvantage. So in parallel, we were thinking about how could we actually use 3D printed plastic, to put it very simple, as formwork. And with this, we had eggshell as a starting point, which was then later on the PhD of Joris Burger under my supervision, where we started to say, okay, with smart dynamic casting, we don't have any formwork pressure. So why can't we just use something very, very thin, almost like an eggshell or something very brittle to pour the concrete inside? So we started to develop together with students within the MAS of digital fabrication at the ETH Zurich. Here, some of the first tests that were done just to explore how wild can we go? How much can we actually do with this system? And it ended up with a small catalog of which you can see some of it here, which is not about any kind of structural optimization or calculation at this stage, but just simply to understand, does it really work, this mindset that we have no formwork pressure, and it worked really, really fast. So with this, we were contacted by Basler Hofmann, one of the leading structural engineering companies in Switzerland, and they asked us if we would like to do a demonstrator outside of their premises and in Esslingen, and we said yes, and we actually said yes a little bit fast because we realized there were many things we did not yet know. For instance, we were not very good in printing large-scale polymers because in the moment you start to print in large scale, you also have a warping effect of the material, and it starts to delaminate, a huge problem that we had to tackle. Also the printing time and the points that we had to send. So there's a lot of computational work in the background that we had to solve. But also when you look at these images here, you see that the formwork has a little bit of a star shape inside. And this was actually to avoid the warping of the material. So it's not something we thought, it would be beautiful with some kind of a pattern, but it was actually coming out of the fabrication process itself that we could avoid the delamination through that. And then you see a little bit the generation of these different tests of prototypes that we did, because we really see a big value in always scaling up the processes. I always say everything that works up to a meter is not a proof of evidence that things will work, especially with these set-on-demand processes. So everything we did when we had developed something, we always went up in scale, up to this 2-meter height. So we knew this can really function. Then, of course, a lot of rationalization has to happen when you need to do a real scale element that needs to go on site and the project is kind of less than a year to develop. And here you see that we actually decided not to have this conglomerate of printing, casting, and reinforcement all at the same time, but actually taking the things apart. So here you see the formwork, the reinforcement, and then you see the final element on the side. And here, this is not one of the last elements, but I think it shows very beautifully how thin this formwork was initially. In fact, it was a good first proof of concept to prove that we can do a full-scale column using 1.5 millimeter thin 3D printed formwork and using the digital casting system. So it was really a way to demonstrate that this system is actually working. Now, then we went on to say, okay, can we also use it for optimized rib slabs? And what about this complexity that we have with this set-on-demand process, which doesn't really allow you to cast in large areas? So we had to kind of step one step back and say, okay, but we could actually start developing tools to make more optimized structures where we can save up to 50% of materials in the slab. And we all know the slab is a very interesting area to save materials, especially given that we can go up to 50% less. So we did a series of tests, and this was in a collaboration with Walter Kaufmann's group at the ETH in Zurich, structural engineer. And we did a series of tests with the slab to really provide evidence that there was the same structural strength within a standard slab as well as our non-standard slab. And they have similar performance. And with this, we could also say, okay, with these formworks, we can produce concrete structures with 40% less. Now, at the same time that we are doing this, of course, we are working with plastic. Plastic is not the best thing to use in the world. And we started to look into, together with a technical university, how to recycle the plastic. And this goes through this process of formwork removal. Then you need to clean it. You spend a lot of water. Then you need to shred it. Then you shred the pellets. And then you regranulate the entire thing before you can actually reprint. And you cannot fully use a full recycled material. You always have to combine it with virgin materials. So these are things that, of course, start to linger in your head. Am I greenwashing? Is this okay? Can I really use this system? You save material, but you then again have a kind of a feedback to yourself saying, yeah, but this is a plastic formwork, and this whole process is actually not sustainable in a scale. Nonetheless, we went on to test this in the Eggshell Pavilion that was then exhibited at the Vitra Design Museum in Europe at this site. And this was also part of, let's say, part of the MAS, where students together with structural engineers were defining both the columns as well as the slab system as to be a disassembled system. Again, in this process, we took the material from other columns that we had been produced. They were shredded in the process I showed you, and then they were printed and cast with the set-on-demand. So in this case, we remained with set-on-demand systems for the control of the hydrostatic pressure. And here you get an idea of the further development of the digital casting system, which was then further developed to have an inline control so we can also understand what is the torque of the material, so we can change the speed of casting throughout the process. And then you see how the formworks are removed. And then again, as I showed you before with the slab was produced, but using ordinary SCC. Finally looking like this, and now it's been disassembled again, and is now standing at the prefab plant that sponsored us for the project. So I guess you sense there is a bit of a criticism to my own work in the sense that plastic is maybe not the best to use, and if you want to use it, we need to develop systems, and this we have been doing in the side of how to actually, I call it the chocolate bunny system, that you actually have two sides and you can take them apart. And this, of course, is to be further developed. However, I thought, okay, since we can use so thin material with our set-on-demand system, why not use paper? So there was a lecture at the ETH where Josef Choma, a guy, the professor, from the United States. He came and he showed a lot of folding techniques, and I was like, maybe we can use these folding techniques together. So I approached him and we set up a small workshop together to use paper folding as formwork for concrete. And of course, paper is interesting because it's low cost, it's easy to recycle, it's easy available, and it has a huge design flexibility, which we've also seen in the historical context of Josef Albers and David Hoffman that have been developing a lot of computational models for folding paper. So Anna Sabo, here on the picture, was doing her PhD also in my co-supervision. And I went to her and I said, can we not test your digital casting material that you're now developing? And we cast paper, we use paper as a formwork. And I find this a very magic moment personally, because here you really see how easily it is to just take this very thin foil that has a wax coating, fold it up in this bistable structure into a formwork. And we tested this also on columns, and it was incredibly robust. And we just did some fun tests, and you see some of them bulging at certain moments. So of course, there's also a number of constraints here, but then also again, with my kind of idea that nothing works if it's not 2 meters, we also tried to make this taller column. This was made, you see the lines from the formwork because we couldn't get big enough paper, but it shows that it's actually possible to also cast a 2-meter column using millimeter thin paper. Again, there's always this thing about industrial applications, and I think there is something that I've learned over the years is the industry is not really ready for things that are too complex to do. And automation, especially in Switzerland, is taken a bit with care, especially when it's completely new processes that have to be implemented. So even though we've worked with 2 industry partners setting up the entire digital casting system, there is still people missing who can actually control and understand how to work with them. So this is one of the reasons why this is not really making an impasse in the industry. So with this in mind, I thought, okay, we do a lot of things, but can we actually do something that could make an impact relatively soon and not be so disruptive within the industry? And that's when I asked Fabio Amicarelli, who is now my partner in my startup, but also the PhD student and the one behind some of the work I show now, where I asked him to develop folding techniques for slabs using ordinary SCC. And everything was starting up with a workshop I did prior, and then we said, okay, we can use the normal formwork, and we just go back to this idea of the formwork inlay, which we normally do with wood or styrofoam, but we do it with paper. So here you see kind of the process. You have a flat sheet of paper, you have a folding pattern, you place it inside of this wooden frame, and then you can cast your concrete inside. So that's essentially what we're doing. And then, of course, what we are doing on the side is we are developing a digital design software where we can also have the structural design included within the system. But of course, a lot of things have to be tested first. And here you see a section of one of the first slabs that we did. And we started in a way to see how can we use this folding pattern also to guide us in the structural concept. And this was kind of the design driver behind most of the work we do with Foldcast now, is really to use the folding not solely as a kind of ornamental or nice thing to do, but really as a driver for optimizing the structures and building in the structural concepts. So as you see here, the red lines are actually the beams of the structure itself. And we did this concept we transferred to these 2 different systems, which where we are using parallel ribs in the slab Y and in the slab X with the cross ribs. And within this, we also developed a reinforcement strategy that works for both systems. Very simple, nothing magic about it. And it includes this double layer of reinforced grit and U-bars that transfer the load from the rib to the upper plate. Series of studies were then done in our lab. And then we also work together with Oost-Rapperswil because I somehow think it's very important to all the time thinking of what are we doing with the concrete also. So we developed a concrete mixed design together with Oost-Rapperswil and SUPSI, which are the technical universities in Switzerland, to have a material that reduced the amount of, let's say, virgin cement and used recycled aggregates. And this we tested at the prefab plant with the paper formwork, which then, again, you see here we have this underlay of cardboard, and then we have our thin wax-coated paper on top. And this was one of the first prototypes we did. And then we did kind of a little checkup to see what is the environmental impact of this. So looking at a normal slab compared to our slab X. And here you see that we were able to reduce 43% of concrete, and we were able to reduce 27% of reinforcement. And again, for the formwork itself, compared to a wooden formwork, would be 67% less impact. And then you see what this could look like in a building, normal office building, as a kind of idea of how to actually structurally optimize. Again, sorry, I need some water. Then, as a next step, we also started asking ourselves if we can use this technology to make staircases. And a first study was done, which is currently being executed in Italy, but these are the first prototypes, where we tested how to use an assembly system for staircases that could reduce materials. And it's a very simple concept with a beam, and you place the staircase steps on top, and in this case, you grout them inside. And again, here, you can see the production, pretty standard process, placing the formwork, casting the concrete. And then the demolding again. And this is then the staircase, and a similar study was done to understand how much could we actually save. And here you see we could save 57% of concrete compared to a standard staircase. Steel was not easy to save in this case. And again, the paper formwork was also less reduced than a normal, let's say, wooden staircase. Nonetheless, it opens up new possibilities of how to think, how you can flexibly actually start casting staircases also in situ. And as already mentioned, this is part of a so-called spin-off that we have in Switzerland, where you can look at the website, and we are together with Fabio Amicarelli, myself, and Ilia Quadranti, structural engineer, moving this forward. And the next step will be to do this in situ, which is a very interesting challenge that will be at the ETH in Zurich as a pavilion, where we are testing how this can actually work in situ and also expand on the design space. Do I still have time, Melody? Yeah? Okay. Because I was also asked to show what we are doing with earth. And earth is, in a way, a very interesting material. For me, it's kind of a natural thing to also look into, because the way you process earth is very similar to concrete, only with the very, very big advantage that it doesn't hydrate inside of your machinery. So that's very nice. And in terms of circularity, I think there is also kind of a need to start pushing the boundaries further. So we started to look at what are the possibilities of earth in digital fabrication. And it's much easier to modify earth. Also, as a kind of layman that is not a material scientist, you simply add water plus minus, and you can change the viscosity pretty easy. Also, it's found everywhere. It's easy to source. And then, of course, it's fully reusable if you don't start adding any cementitious materials inside of it. So we really see it on a global level. We have earth everywhere, both as excavation materials and in different types. And we also have a very strong history of building with earth. And really from this more, let's say, historical, more humble homes up to more historical and religious buildings that have been built over time. Now, I think one might ask why digital, and I think, of course, it's very interesting from my perspective to look into how we can use earth as a temporary formwork and recycle it again. So on one hand, the material efficiency, but also how we can start integrating new designs that are structurally optimized and through this customization ability that we have. And as already said, it's very easy to modify this material compared to concrete. 3D printing, you can really quickly get into a work that operates easily. And then, of course, to do that, you also need to, again, understand what are the design constraints of your printing properties. So how far can you have overhangs and so forth. So what I will show you now are 3 projects that we've been doing, partly as a part of all of them, including PhD students, but also students from the Accademia, the Architectura in Mendrisio. And the first one is the one where we looked at, can we actually upscale 3D printed earth as formworks? And here it was essentially saying, can we translate what we did with eggshell into earth? And of course, easier said than done, but what we understood is that the earth on its own is actually not really able to sustain very high. So if you look at this video here, where we print 40 centimeters, 30, 40 centimeters, you see what happens? It collapses, of course. So not what you want. So I think there is a kind of moment of let's say, failure, which is in this area of 30, 40 centimeters. You can't build higher with earth unless you let it dry and then you reprint on top of it. So what we tried together with my colleague, Professor Döffler in TU Munich, within the AMC network in Europe, and with the school, with the technical school in Braunschweig, also with Norman Huck, we set up a team of PhD students to investigate if we could, on one hand, use earth as a formwork with the set-on-demand concrete, but also how could we print around reinforcements. So it was kind of a research done from 3 different points of view, where we also aimed to print with 2 robots around the reinforcement. And then the filling, in this case, is done manually with a less well done set-on-demand concrete, but nevertheless, it works. So, okay. So many of the things we do, we also try to integrate into the teachings. I'm just going to give you a small insight on how we are running this as an elective course also at the architectural school in Mendrisio, where we really try to teach students the fundamentals of the material, in this case, earth, before they actually start to work with it in digital processes. I really have the strong belief if you don't understand the material, you can't really translate it into any type of process. So you need to always keep these 2 things very tight to each other. And I also think that it's in this intersection that new innovations can emerge, if you have that sense. Now here, with this example, the students then started to develop small tests where they were understanding also after doing the first series of manual tests, they went into testing what can we actually print with this system, and to understand how can we change the geometry, or how can we change the speed to change the geometry of the final element. So you cannot always design digitally what comes out of the nozzle, but you can feed it back into your system so you know which speed, which nozzle size generates different designs. And with this, they then took on this assembly system where they made a column out of elements. that was then finally looking like this. And the idea was, in this case, to use it as a lost formwork. And you see at the bottom of the column, you see some concrete tipping out, but we just casted the lower part to be able to disassemble the whole thing again. Same concept, same principle, we then took on in our winter school, Earth to Earth. But here, we didn't want to cast with concrete. And we worked together with David Jenny, a colleague of mine with whom I'm running a series of winter schools from the ZHAW in Zurich, and with Oxara, which is a startup in Switzerland that looks into earth-based materials for construction. And here you see, we take kind of this unstabilized 3D printing earth, and then we cast not concrete, but earth inside of the formwork. And I will illustrate this through this video, and you will see the process again. So this is at the Academy of Architecture in Medrisio. We had students from Medrisio as well as students from the ZHAW. Students were learning how to prepare the entire site. They learned how to develop the earth-based material and the printing process. And then we had a sort of a small design competition where the students came up with different designs of how the staircase could look like. And within 5 days, we were able to design, build, and cast the entire system. And it's the back of the Tucconi building in Medrisio where a new building is planned to be. So this is why we didn't want to also cast anything that was going to stay, but more something that could be there for a short period of time. And then, of course, as it was planned to be ephemeral, you see here the first day, and then after 382 days, how this has disappeared. And today, it's not there anymore at all. And then the question is, what else can we do with Earth? So within the doctoral research of Sasha Kutaja and my group, we are questioning again the thing of a slab. And many of you maybe know this project of Kundo, where she's using these, let's say, found objects to optimize concrete slabs in India. Very amazing and beautiful work, in my opinion. And we took this as an inspiration to say, wow, okay, maybe we can do similar thing with unfired earth. So we took this concept and then we tried to translate it into this kind of constraint of the material of only wanting to be printed up to 40 centimeters. So instead we said, okay, what are the advantages? And we started developing these cups, I call them kind of. And here you can see kind of a sketch of how this could look like. And then finally, how the process works. We print these elements, we place the reinforcement, and then we cast the concrete in this case. And this is Sasha Kutaja from my group, and then you see how we've developed a small software tool within Grasshopper to also control the design parametrically in conjunction with the structural inputs that we give. And then in the lab, under relatively simple conditions, we are able to cast. And then, of course, we have these different load types. So depending on the load type, you can do different patterns with the primary and the secondary structure, both as wall as slab configurations. And here you see the prep of the earth and the placing inside of the pump. So you can see there is a huge resemblance between what I showed you in the first project of smart dynamic casting to the way we actually work with earth now. And this is ongoing research, so it's not coming to the full end yet. We're doing different studies of where we're trying to understand, can we keep the earth in place, or do we have to take it off? And both is very, taking off the earth is very easy. You submerge it in water, or you just spray it off, and then you have the slurry, and you let it dry, and you can reprint with the same material. or if it can stay in place, it of course has a lot of advantages in terms of inner climate. And here you see some of the design studies that have been done in a smaller scale to see what are the possibilities of this system. And the last thing I will show you, so I'm almost done, don't worry, is what we are looking at the moment with a former collaborator of this university, so Sevgi Altun, where we are asking ourselves, can we take this even further, this idea of circularity, this idea of not generating waste? So we go from slipforming, which was almost no formwork, then we went into plastic, which has its own problem, paper, and earth, and now we're looking into granular formwork to ask ourselves the question if we can use waste from demolition to actually produce formworks for concrete. And of course, this requires a lot of fundamental work to be understood. And here you see some of the studies we've been doing in sand. They are being scanned, and this is then being fed into a model where we start to understand upfront what we can design with the system, which is, of course, what is the interesting part for the architects, is to know what is it I can do with it, how can I design with it. And this, of course, needs to be simulated from a digital to a physical system. As a first kind of study with students, we did brick waste, where we developed this demolition waste classification, then demolition waste characterization, and then what are the design constraints, and then we used augmented reality to shape the formworks manually in this case. And first to understand the stone, and then we went into understanding what is the, let's say, geometry, the angle of repose that you can gain with this material, because that is the uppermost design constraint of your system. Then a series of smaller studies were done, and then we were understanding what is the minimal maximum slope, and then with machine learning models, we were able to predict a number of different designs, choosing one which was compared to a standard, let's say, spiral staircase, could save up to 35% of material, concrete. And then the students started casting 3 steps in this case, using the augmentation to shape and cast. And finally, they had these 3 steps where, of course, we have the leftover from the formwork, so it's a kind of a new aesthetic. And the big question is, do we keep it, do we not keep it? But I think it's a very beautiful way to start to rethink how we construct certain things. Of course, we have discussions ongoing, do we put a intermediate foil in between or not, or is the granular material needs to be scaled, so it's part of the structure. So there are many things that we are questioning right now, and this is really a new research project, but I thought it was nice to show, as it's one of the people that have been here at the university, where we are asking how we can build less, not generating any waste at all. And with this, I would like to come to an important moment, is of course that I didn't do this alone. This is part of work done with people from the ETH that are very dear colleagues of mine still, but also from my USI team in Medrisio. And with this, I say thank you for your attention.
Well, thank you very much, Ena, for the very impressive and inspiring sharing. I mean, recalling when we were conceiving the lecture series in the beginning, so our title or our theme this year is like architecture as work for the fall semester, and we always try to bring something about technology in there, and I think your work actually really integrated both from architecture as a verb, as an action, as a craft, and then also the technology aspect, not only as in how technology itself or what it can do, but actually what we can actually do together with them, and the important message of sustainability as well. So I actually checked all the things that our school actually wants to promote it. So thank you very much for that. And
I'm happy.
yes, I guess we don't have a lot of time, about like 50 minutes more or less, but I'm sure there might be some questions or thoughts. And in the audience, okay, we have Adam there right away. Yes.
Anna, thank you for like a fantastic lecture. It's tremendously, like at certain moments, really moving to see this kind of work, and it's interesting in conjunction with other movements in architecture where we see very high-tech solutions unlocking forgotten or redundant building techniques and making them relevant again in a new way. So one can, in that light, I guess you could think of the rediscovery of massive stone construction by group work in London, or people who are doing, I think, it's an ArchiCAD who were experimenting with, on an Autodesk, who were experimenting with visual recognition of low-grade timber and how to analyze, how to robotically arrange it in a way that was structurally sound. And so there's these moments we see here where you've taken something very high-tech like digital fabrication and combined it with something very straightforward like mud, and you've shown how you can create an entirely new process that is both retrieval of something old and a kind of high-tech acupuncture where something new comes in. Does this, in a way, fit into a kind of design philosophy? Do you see a sort of general strategy here that can be applied either in fields adjacent to yours or in completely different parts of architecture? And if so, do you have any kind of like suggestions for how we or students can reimagine our approach along these lines?
Good question. So I'm not sure exactly. So maybe the question is how I can see this in other areas within architecture, essentially. That's your question.
Yeah, like what strategic advice can you give for how to recognize a problem or how to recognize a potential solution that has an unexpected?
I think it's a very good question, because it's the problem. What is the problem in architecture? I think it's very, very big, and there are many in this room that I know also work in fields trying to tackle these problems socially, but also economically, politically. So I think, where do we start with change? And it's a question that we are asking also a lot, especially with my colleagues from the ETH. We're really looking at how can we engage with industry, and it's a bit of a chicken and egg problem. How do you implement this? Because on one end, you see industry being scared of changing a running system, and on the other hand, in the case of concrete, it's so damn cheap that nobody cares about saving on it. Nobody cares. Nobody understands the impact of actually reducing. Of course, there are systems in prefab applications that easily allow to save concrete, but it's always the same question. It's I think, who's going to pay the taxes for this in the end of the day? And I feel like it goes even a level higher. So we can teach a lot in school and hope kind of from the bottom to make some influence. But then on the other hand, everything is about the cost and the speed, right? We know it. It's not new. So how do we impact that? And that is not me alone. I think this is more like there has to be a kind of a stop and watch, and what is it we're actually doing? And this city here is a beautiful example of how much we actually built, and how are you going to control this? And how are you going to impact this? If I would know it, I would do it. I think you can only go step by step, if I'm honest. If not, I would feel super weird saying that I would have the solution for this very, very complex problem.
Can I ask a just very quick follow-up, which is just it's a very, very small technical question, just because I didn't know if I'd misunderstood something. With the origami approach, you had a paper formwork,
yes,
and concrete flows into it.
Yes.
But the paper is strong enough to resist a kind of conventional concrete slurry, or
Yes.
does the concrete have to be poured in slow enough
No,
that
no.
it's partially
So-
setting?
So that you understood correctly, it's paper, and of course, in small scale, you don't need any kind of support underneath. And then as you scale up, of course, when you cast a ton of concrete like we did, then you need a few supports underneath, but not very much, and that's also cardboard. So we cut everything with the machine I showed you, and then we fold it on top. So it's just cardboard. It's cardboard with this, to get a super nice surface, we use this wax-coated paper. So it's just that.
Yeah, to illustrate the problem of implementation, I can come with a little story of my own. I started a school project here 10 years ago,
Yeah.
here in Hong Kong, and I wanted to implement bubble deck as a technology
Yeah.
for the slabs, because we all know when you start to build a bit higher, it's in the deck that you can make some real savings in terms of concrete. And that technology was, we used it in our firm in Harper in Iceland and things like that. So I wanted to import it here. And we went to a building department with it, and they told us, well, you need to get approval for this. And so it went through TechSec, and I quickly abandoned the idea of building with it because it went very slow.
Yeah.
And it has been approved this year
Yeah.
to be used in Hong Kong. So it took 10 years
Yeah.
to get the bubble deck technology
Yeah.
approved in Hong Kong.
Yeah.
It's not as sexy a technology as the ones you're developing, because the saving is inside the slab.
Yeah.
You cast the concrete with balloons inside of it, in between the rebars.
Yeah.
But it does achieve a 30 to 40%
Yeah.
saving in concrete. So it's also a remarkable technological, if a bit simpler, let's say, to
Yeah.
implement, and only for the deck.
Yeah.
But it is now approved in Hong Kong, for your information. So it's the small steps at the time,
Yeah.
and yeah, you need to do the research before you can start to get things implemented and into the real projects.
Thanks, Claude, for this add-on. Maybe I can come to you when we need it approved here. Yes.
Yeah, wonderful. Let's get a couple questions from the students. Yeah, I'll collect that one and then one over here. Yeah, please.
Oh, thank you for inspiring talking. I think I have two questions. One is like, I thought lots of your work is done in the factory. So I want to ask, based on your experience, what is the biggest challenges when moving from the lab-based to the real construction, especially in the low resources environment? And the second one is like, actually, when we do the project in the rural area, we are more consider about the community participation. So, I want to ask that, how can we balance the high efficiency digital fabrication that with the meaningful of community participation, especially when I think both of them are very important, but often pull in the different directions. Thank you.
Thank you. So you asked two questions. I start with the one of what do I see as the biggest challenges for bringing this in situ. Is this correct, what I understood? Yeah. So in terms of the first project that I showed, which is slipforming, it already exists in situ, as you probably know. But as soon as you start to manipulate with material, then there is a lot of constraints coming around temperatures. So, for instance, what we did with smart dynamic casting, which you don't see here in this video, is we did the so-called digital penetration test. So after we had mixed our concrete mix in the morning, we would do a series of tests with a small robotically controlled digital potentiometer, and through this we got the curve of the hydration. And with this you can define the speed of which you construct. And this is really quite innovative, because in the construction sector with slipforming, what they do is, I went to the site a few times, and there's this guy who worked there for like 50 years, and he just goes with a kind of wooden stick into the formwork, and then he shouts down and says, "We are ready for the next batch." very simple in a way. So I think it can be scaled up either with high-tech or more low-tech manners, as I just illustrated, and I think there is an intermediate scale of this slip forming process. So I don't think it's an impossible mission. I think it's a mission that could happen and is already happening. I didn't show this today, but I mean, there is a whole historical predecessor of slip forming with complex formworks that has developed. I can give that online, maybe that lecture. But yeah, so I think that biggest challenge there is controlling the hydration and the precision of the mix design in smart dynamic casting. And that's why we went away from it, because it's a little bit irrobust. If you then, let's say now we jump to the paper, which we are currently challenging to do in situ, rain and paper, not the best combi. So you would need to have a kind of tent on top to make sure it doesn't start to warp. You have to work fast. How do you step on it? We are developing strategies of easily being able to assess the formwork because it's a 7 by 7 meter slab. So how do you assess a formwork that is not made to step on fully? Because if you step on it wrong, of course it will break. So these are some of the challenges that we will have in situ. And of course, in a contained prefab environment, these are not problems. These are easy things to go about. So I think for the paper formwork, it's really about accessibility, placing the reinforcement and ensuring that it doesn't start to warp in the rain. It's pretty clear. Yeah, and for more than that, I think that's it. And then going to the next question, which is more about how do I see this in more, let's say, rural areas, for instance, with the earth. I think there it's a super good question, and I think it's also a very dangerous thing to, you already see it with the industry in Switzerland, which is actually very efficient, very automated. You always have to be careful coming in with your wagon, right? And then you say, now we are all going to be robotic and we are all going to do this thing digitally. I think you have to analyze what environment are you in, what can you bring, and where is that world in between, right? So for instance, the reason I showed the staircase is because that is exactly doing that. You know, it's like you use a bit of augmentation, you use some smart tools available, but you don't really need the robot. You need your hands. And then you can start using the digital technology for what it is very good at in certain areas and human skills at what it is good at in that place. I don't think you need to bring a robot everywhere. I'm actually not really a fan of that. So I think it's all the time asking these questions to yourself. Where am I? Which context am I in? Yeah.
Yeah. Well, thank you very much. I think we have one last question here. Yes, please.
Hi, Ena, thanks for your impressive presentation.
I don't hear you.
I think you are exploring 3 types of molds by different materials like paper, earth, and timber. And which one do you think perform better, like considering the cost, carbon saving, and the construction time?
Can you repeat? Because I really can't hear.
Formwork like using traditional timber, earth, and paper. Between the 3, which are better?
Yeah. So the way we evaluate it, we are using an LCA tool. We are working together with the sustainability group at the ETH, who are also developing these agile, sustainable tools where we can input a number of, let's say, variables, and then we compare. So we try to compare apples with apples in these schemes that I showed you before. And through this, of course, you start at the moment of casting. So we don't consider everything before, like the cutting down of the tree, and we just take from the moment we take the wood from the shop into the lab. This is where we compare from. And then we stop at the end of the production, right? So we could also go further. What is CO2 emission of trees, and as the whole spectrum. So we are only looking at a section because we are not the group for developing agile sustainability tools. So in that sense, we compare what would this have been if I made it out of wood, with the CO2 emissions that are given public, and then we add these into our models, the same with the paper, the same with the plastic, and then we start comparing these things. We're currently running a study on the impact of plastic versus earth. So we are continuing to build up this catalog of understanding. So I cannot give you the final answer yet, but there is definitely some indication that earth, paper, and gravel has a much lower CO2 emission as a formwork than wood. You also saw it on the calculations. Yeah. So.
Okay, well, thank you very much. I guess, is there any other last question? If not, we'll give a big hand to Ena, and thank you very much. And on behalf of the School of Architecture, a small gift for you.
Thank you very much.
Thank you.
And then maybe last word too. So thank you everybody for sitting in the middle of the day. Everybody's hungry, I suppose. So thank you very much for being here.
Thank you.